The title of my report has small changes. We will tell about semigroups generated by difference equations of retarded type and corresponding generalized random processes. It is practically the same title, and the plan of my report is the following. Firstly, we consider a semigroup generated by functional differential equation with retarded terms and a cylindric measure on trajectory spaces. We investigate the bijection mapping of the space of operator valued functions onto the set of complex valued, finitely additive, cylindrical measures on the space of trajectories. And finally, we consider the representation of solutions to evolutionary equations by random processes and Feynman-Katz formulas. Let us firstly consider the model initial value problem for the retarded type functional differential equations. We will consider the simplest case. Let us consider the functional differential equation 1, linear functional differential equations with the retard term of such type, and we equip this equation on the semi-x of real line with the following initial condition. The function is given on the initial segment, on the segment of retarding argument. Here h is the retarded time, is a positive constant. A and B is the complex constants. The initial condition phi is the function from the following Sobolev space, complex values function from the Sobolev space on the segment of retarding argument. And U is unknown function. We now consider this simplest example of the equation with retarding argument. In more general case, we can consider such function with values in some Banach space instead of complex plane. But now let us consider the simplest case to analyze the phase space for trajectory of processes which be able to describe this equation with memory. To define the solution of this problem, we should introduce the following functional spaces. For a given real numbers gamma and A, we can introduce the following space of measurable complex valued function, which is square integrable with the following exponential weight. And the Sobolev, the weighted Sobolev space is the function from this space which has the generalized derivative from the same space. The norm in this space is presented by the following expression. And now we can define the solution of the initial value problem 1, 2. A function u is called gamma solution of the initial value problem 1, 2, if this function belongs to this weighted Sobolev space with weight gamma and satisfies the equality 1 and condition 2. Then we can obtain the following result on the solvability of this problem, and therefore we can define the semigroup generated by the considered functional differential equation. Theorem 1 states there is a number gamma 0 such that the following statement holds. For every parameter gamma greater than gamma 0, there is a constant C gamma, such that for every initial function phi from this Sobolev space, there is a unique gamma solution U of initial value problem 1, 2, and moreover, the norm of this gamma solution in the weighted Sobolev space admits the following estimation by the norm of initial data. Now I note that this parameter gamma can be obtained from the following condition. This condition this condition must be hold for sufficiently large gamma, since we have this this decay exponent, and this term is not so large with growth of with increasing of parameter gamma 0. A corollary 1 from this theorem. Let gamma be a constant from the theorem 1, then there is a bounded linear operator V sub gamma 0, which mapping the space of initial data, the Sobolev space of initial data, into the weighted Sobolev space of solution of the problem 1, 2, such that for any initial data from the Sobolev space, its image, the image of this function under this operator, is the solution of problem 1, 2, which admits the following estimate. Corollary 2 states that if gamma 0 is a constant from the theorem 1, then there is a strongly continuous semigroup U acting in the Hilbert space of initial datas, and the action of this semigroup is defined by the following way. We should consider the image of initial function phi, which is the solution of problem 1, 2, and we should restrict the solution on the segment of the length h from t minus h to t, and if t belongs to the positive semi-x, then this action is the action of semigroup. And according to the theorem 1, this semigroup admits the following estimation on the growth of the norm of the operators. Thus, we construct the semigroup generated by functional differential equation with one retarding term. Let us consider the sufficiently simple scheme of the proof of these statements. We can, firstly, we should introduce the following changing of this problem. we check the initial data, and we can solve this problem in the following way. We put u equal v plus, we put u equal v plus a function j phi such that the restriction of j phi on the segment minus h0 satisfies the initial condition phi of t if t belongs to this segment, and maybe this following on the positive semi-x, then it is sufficiently smooth function which has a good decreasing as t tends to infinity, such that this function belongs to Sobolev weighted Sobolev space W gamma with any gamma. And after that, U is a solution of the initial problem 1, 2, if and only if the function V satisfies the following condition with function f phi, which is given by the action of these operators on the function j. After that, we can study the problem 1 prime 2 prime, and we substitute the unknown function v in the following form. Now we conclude that function v belongs to the weighted Sobolev space if and only if the function w belongs to the usual Sobolev space without weight. And let us apply the Duhamel approach. We can consider the third and fourth term in the equation 1 prime as the perturbation of the first initial equation, and after that we can substitute the following expression for the function w with unknown function z. Unknown function z belongs to this space. We should we put z equal to 0 on the negative semi-x, and it is a known function on the positive semi-x. Then the function w is the convolution of unknown function z with the following function. And after that we substitute the function w to the equation for it, and this equation is equivalent to the following equality for the unknown function z from this space. Now the operator sh is the shift operator sh on x of t is equal to x of t minus h. This is sh. And the operator sh is bounded operator in the space L2. The operator of convolution can be estimated, and the considered problem now is equivalent to the following operator operator equation where K gamma is given by the following expression. And if the norm of K gamma less than 1, then we can obtain the solution in the following form. And the condition of that norm of K less than 1 is equivalent to the following condition. Do you see the condition in the below of this slide? Is it sufficiently observable? Дорогие коллеги, видно внизу слайда?
Sure.
Хорошо. Okay. And this is the explanation of our result about the semigroup generated by the functional differential equation. And now the aim of our consideration is to obtain the one-to-one correspondence between the semigroup acting in the Hilbert space and the random process with values in the coordinate space. For heat equation or Fokker-Planck equation, it is well-known theory, and now we should extend the notion of random process such that the extended random process can be described an arbitrary C0 semigroup in the space L2 of R, L2 of R in power G, or in other Hilbert spaces. It should be known that Feynman complex-valued finitely additive measure was introduced to description of Schrödinger equation. Feynman, Nelson introduced this measure. Professor Smolyanov and Professor Shogulidze write a book, Continuальные интегралы. In this book, the description of this mathematical construction is given, is developed. To construct the analog of Feynman measure for the arbitrary semigroup, we introduce some extension of random process notion. Let R be a ring of subset of a set E, and A be a sigma algebra which is generated by this ring. Let omega F and P be a triplet which is a probability space. Definition 1. Random variable with values in the set E equipped with a sigma algebra of subset A is a measurable mapping psi from omega to E. The measurability condition is the following. For any set from the ring, its preimage belongs to the sigma algebra F. Sigma algebra F. Definition 2. A distribution of random variable Xi is a measure mu sub Xi on the measurable space E equipped with sigma algebra A, which is defined by the following equality. Mu psi of A is the measure P on the preimage of A. Definition 3. Evaluate random process is a family of random variables, which is parameterized by parameter T from the set T capital from real line with values in a measurable space E with sigma algebra A that are defined on the same probability space omega. let XCT be evaluate random processes. Then for any finite subset T1 Tn from the set T capital, the symbol A in power n denotes the sigma algebra, which is generated by the collection of the following simplest sets: the direct Cartesian product of n exemplars from set from the algebra A. It is the simplest sets, and on this the collection of these simplest sets, we define the minimal sigma algebra containing these simplest sets. Definition 4. For every finite set of time indexes, T1, Tn, a finite dimensional distribution, P T1, Tn, of random process Xi is a distribution of random vectors in the n power of E equipped with the sigma algebra in power of n. It is a vector valued random variable in this measurable space. And a trajectory of evaluate random process is the function of argument t from T capital with some fixed argument omega from the omega capital. This is the random realization of random process as a trajectory. The symbol m from T to E denote the set of mapping from T to E. Let us consider cylindrical set of all of such mappings. In the space of all of such mappings, the set is called cylindrical if the set can be presented in the following way. For a finite collection of T from T capital, we put the following finite number of conditions, and any set B sub k belongs to the algebra A. The collection of these sets B is called the base of cylindrical set, and T called time indexes of cylindrical set. This cylindrical sets, the collection of these cylindrical sets is denoted by the following symbol, and lemma 1 states the following: let A capital be an algebra. It is not obvious to be sigma algebra, which is generated by a ring A of subsets of the set E. Then the collection of cylindrical set is a semi-algebra. Semi-algebra is the semi-ring with unity. Semi-ring with unity E. Cylindrical algebra CIL is the minimal algebra generated by the semi-algebra CIL. A complex valued finitely additive measure defined on the cylindrical algebra is called a cylindrical measure. The cylindrical measure is a complex valued finitely additive measure on this cylindrical algebra. The space of cylindrical measures is a linear space, which is denoted by the following symbols. For example, cylindrical measure is the final measure which was introduced by Feynman, Nelson, and Smolyanov as the function of a set which is defined on the cylindrical algebra. let A in power T be a sigma algebra generated by all algebra of cylindrical set. Kolmogorov theorem on the product of measures states the following. Let E be a barrel measurable space. Let for every finite collection T1, Tn from the set T capital, there is a probability measure mu T1, Tn on the following measurable space for every n. Then there is a probability measure mu on the following space, the space of all trajectories equipped with this sigma algebra of subset generated by the algebra of cylindrical set. This measure on the space of whole trajectories is the measure such that its values on any cylindrical set coincides with the value of this measure on the base of this set. The existence of such probability measure is equivalent to the following condition, that the family of measures, this family parameterized by arbitrary natural n and arbitrary finite subset T1, Tn from T capital, and all of these measures should satisfy the following matching conditions. First condition is the following, and second condition is the following. This theorem was proved by Kolmogorov for the probability space and real random process, which is described by probability space. And now we introduce some extension of this notion. Definition 6. A generalized random variable with values in the space E is a complex valued finitely additive measure on the measurable space E equipped with algebra A. Definition 7. A cylindrical random process with values in the space E is a complex valued finitely additive measure on a measurable space of all trajectories equipped with the algebra of cylindrical subset. This definition is introduced to describe the Feynman measure as the generalized random process. Lemma 2 states that there is a one-to-one correspondence between the space of cylindrical measures and families of generalized measures, satisfying the matching condition from Kolmogorov theorem. The lemma 2 is the restriction of the Kolmogorov theorem, since we should know the aim to prove the sigma additivity of this measure. Therefore, the statement of lemma 2 is sufficiently simpler than the statement of Kolmogorov theorem. The definition of a cylindrical stochastic process allows each C0 semigroup to semigroup of operators acting in the space of function which is measurable with respect to the ring A on the set E, and quadratically integrable with some measure on this ring to compare generalized random processes and analyze the processes of the semigroups in the term of properties of the corresponding random processes. Let us introduce some functional spaces. Let E be a locally convex space and R be a ring of its subsets. A of R be an algebra generated by this ring. Let lambda is the measure, is a positive measure which is defined on the ring R. Lambda can be finitely additive measure. If it's a countable additive measure, it is very good, but it can be finitely additive. And this measure is also locally finite and sigma finite and complete measure on this measurable space. Let us introduce the linear space of simple function, linear space of simple measurable function. This is a space of linear combination of indicator function of a set bk from this ring R. This is a usual simple function, and we can define the Hermitian sesquilinear form on this linear space of simple function, such that the scalar product of two indicator function is equal to the measure of its intersection for any set from the ring R, and by the linearity we can extend this equality onto the whole space of simple function by the following way. After that, we conclude that this function 0, 2 is a Hermitian non-negative form on the linear space. But this form is degenerate, and function f and g is called equivalent, are called equivalent if the following equality holds. After the factorization of the space of sim functions by the equivalence relation, we obtain the linear space of equivalence classes, which is pre-Hilbert space with the inner product, which is defined by this form. And the completion of this pre-Hilbert space is a Hilbert space of square integrable functions. And this is a Hilbert space. And now we consider the space of simple function, and we equipped it with the following functional, and this functional is the seminorm on the linear space. After the factorization of the linear space of simple functions by the set of zeros of this seminorm, we obtain the norm space of class of equivalence. And the completion of this norm space with respect to the norm is the space L infinity of complex valued function on this space E, which is measurable with respect to the algebra A of R, and essentially bounded with respect to the measure lambda. And this space exists with the following L infinity norm. Lemma 4 states that every function f from the space L infinity defines the operator of multiplication on this space in the space L2, and this operator admits the following estimation as the operator in the space Hilbert space L2. And now let us construct the bijection between the operator valued functions and measures. Let AAM be an algebra in the space B of H consisting of operator of multiplication on the space from the on the function from the space L infinity. And let M with index AM be a locally convex space of mapping of the semi-X A plus into the Banach space of bounded linear operators by B of H, such that its values at 0 point belongs to this sub-algebra AM of multiplication of bounded measurable function. The topology in this space is generated by the following family of functionals. It is the pointwise with respect to T from semi-X A plus, pointwise weak operator topology for this function. And let M from A plus to E be a linear space of mapping of the space A plus to the space E. This is a space of trajectories, and A small of A capital be a linear space of cylindrical measures on this measurable space. The space of cylindrical measures or cylindrical processes. Now we define the mapping of the space of operator valued function into the space of cylindrical measures. A mapping lambda acts by the following rule. The image of the function f is the measure mu. The measure mu corresponding to the function f takes values on a cylindrical set, which is given by the following equality. The same values, the same equality defines the Wiener measure and the Feynman pseudo-measure where f is a semigroup which is generated by the operator of Laplace, the Laplace operator. Then we obtain the Wiener measure or Feynman pseudo-measure if we choose f is a unitary semigroup generated by imaginary unit times Laplace operator. Since f of 0 is the operator of multiplication, then for n equal to 0, we can we can put the value of measure on the cylindrical set with 1 time indexes and 1 base indexes by the following way. For a bounded set from the ring, we can define the value of measure on the bounded set B by the following equality. On the whole the measure of the whole space of trajectories is equal to some constant m0. It is arbitrary constant, maybe 0, maybe 1 or other. And on the completion of the bounded set, we can introduce the value of measure on the unbounded set by the following equality according to the additivity. And we define the measure on the cylindrical set with one time indices, and the measure on the cylindrical set with base indexes from the ring. And by using the induction, we can extend this function of a set on the whole cylindrical algebra by the following way. In this equation, we can consider the moment Tm. The moment Tm, we can consider the cylindrical set with the condition Xi of Tm belongs to Bm, or Xi of Tm belongs to the complement of Bm, and the sum of these two sets gives the following set. The disjoint union of these two sets gives the following cylindrical set. And this equality is the requirement of the condition of additivity of measure. Lemma 5 states that for every function f from this class, there is a unique measure which belongs to the class of cylindrical measures, satisfying this condition of additivity and this definition 0, 4 and 0, 5. Thus, we obtain the mapping from the space of operator valued function into the space of measures. And now we can lemma 6 note that this mapping is injective. We have the injective mapping from the space of operator valued function into the set of into the space of measure. What is the image of this mapping? To describe the image, we introduce some definitions. Definition 8, a measure mu is called stationary if it is invariant with respect to shift of time indexes. A measure mu is called base continuous if for every time indexes there is a constant m positive, which is dependent on these time indexes, such that for any sets from the ring B0 and Bn, the following estimate take place. Here, beta is a function generated by the measure on the cylindrical sets. Two sets B0 and Bn we fixed, and other on the other sets from base we take the supremum, and this supremum has the following estimate. It is the condition of boundedness, since the square root of measure is equal to the L2 norm of indicated function. And these conditions give the opportunity to describe the image of the measure lambda. Let us note the symbol A sub g. the collection of cylindrical measures which satisfies the condition G, where G is maybe stationary measures or base continuous measures, and its intersection knows by the following way. Lemma 7 states that if measure is base continuous, then the function 0, 8, this function, this is a function of indicator function of sets from the ring, which is bounded with respect to the norm of the indicator of this function. Therefore, this function can be extended on the linear combination of this indicator function, and the space of linear combination of this indicator function is the dense subspace in the Hilbert space of square integrable function. Therefore, the function 0, 8 admits the extension onto the bounded sesquilinear form on the space of linear combination. And lemma 8 states that if the mapping V from the linear subspace of base continuous and stationary measures to the space of operator valued function, which is given by the following way. The values of the sesquilinear form of this operator on the indicator function in the space H is equal to the measure mu on this cylindrical set. There is a mapping which is defined by the following equalities. Thus, if the measure is stationary and base continuous, then this measure defines the operator valued function. And theorem 1 states that if measure is base continuous, then it defines the two parameter family of linear operators, mu of t0, t1, such that the values of these operators on the pair of indicator function is defined by the measure mu on the cylindrical set, which parameter two time indexes and two base indexes. If a measure mu which is stationary and base continuous, defines it, since if the measure is stationary, then this operator 0 and t2, then we can obtain the one parameter family of operators. And lemma 9 states that the image of the mapping lambda consists of only measures which is base continuous and stationary. Therefore, we can define the linear mapping V by the following way. The collection of base continuous linear subspace in the space of all measures, and the mapping V act by the following way, as it defined in the lemma 8. And now we introduce the class of measures which such that the mapping V is injective. In generally, V is not injective mapping. I can explain it in some picture. A measure mu is called Markovian if the families of operators mu with indexes satisfies the following equality. This is the analog of Kolmogorov-Chapman equality for the random processes. I remember that the operators mu with indexes is defined by the following way. The measure mu defines the family of operators. And if these operators, which is defined by the measure mu, satisfy the following conditions, then the measure is called Markovian. And if the condition is satisfied for every P from the algebra, then the measure is called strongly Markovian. If measure mu is Markovian and base continuous, then the measure mu on the collection of cylindrical set can be reconstructed by its restriction onto the following path of cylindrical sets, only cylindrical sets with two-dimensional time indexes and two-dimensional base indexes. Lemma 10 states that any measure from the image of the mapping lambda is Markovian. And theorem 2 states that the image of the mapping lambda coincides with the collection of base continuous, stationary, and Markovian measures in the whole space of measures. Let the mapping V is defined by the following way. The image of measure mu under the action of V is given by the following equality. For t greater than 0 and for t equal to 0, it is given by the following T is arbitrary since the mapping is the inverse to the mapping lambda, and it should be noted the following that I give the picture. If we consider the linear space, this is the linear space of mesh. This is the measure, the space of operator valued function. It is denoted by the following system, and the mapping V is linear mapping, but it is not injective mapping. And the mapping lambda of a function into the space of measure is injective, but is not linear. And we find the nonlinear manifold in this cover is the collection of measures which is stationary, base continuous, and Markovian. The condition of Markovianity is nonlinear condition, such that the mapping, the restriction of the mapping V, which is linear mapping, but not injective mapping. This restriction is injective, and this mapping is bijection. Bijective mapping of this cover in the space of measure onto this space of operator valued function. Maybe I consider the following analog of this for example, V of x y is equal to y. It is linear, but not injective. And lambda of y is, for example, the following. The restriction, this cover is also the image of the mapping lambda, the restriction of the mapping V on this cover is bijective. Therefore, we construct the bijection between the collection of measures and the space of functions. In particular, it is this the function, the operator valued function, can be considered as a semigroup. And now we consider the applying of this approach to Feynman Katz formulas for the perturbation of semigroups, in particular for semigroups which is generated by difference-differential equations. Let us firstly consider Feynman the Trotter's theorem. Let A be a generator of strongly continuous semigroup in Banach space X, and B be a bounded linear operators in the space X. Then the sum of these two operators is the generator of C0 semigroup, and the semigroup which is generated by this sum can be approximated by the following iteration of the product of semigroups. It is not semigroup, but its iteration converges to the semigroup in the strong operator topology uniformly on the segment 0 T capital. This statement gives the opportunity to Feynman and Katz to introduce the Feynman-Katz formula in the following case. Let X in the space L2 of R, Hilbert space, and operator A be Laplace operator, operator A be Laplace operator, and B is bounded operator of multiplication of bounded continuous function. Then the Trotter formula for the perturbed semigroup is the well-known Feynman-Katz formula, and this formula can be presented as the integral with respect to the measure on the space of trajectories. In this good case, this measure is the Wiener measure. This measure is first firstly, we can introduce this measure on the algebra of cylindrical sets by the following way. This is the same formula as in our consideration, where F is the semigroup generated by operator delta. And this measure, which is defined on the semi-algebra of cylindrical sets, is a function of a set which is non-negative, normalized, and countably additive, and it admits the continuation according to the Lebesgue-Carateau scheme to the sigma algebra generated by the semi-algebra, and the continuation is the Wiener measure. Our idea is for arbitrary semigroup U of t in the space H to define the measure mu sub u, which is defined on the algebra of cylindrical set by the following condition. And we can use this measure in the Feynman-Katz formula. Let us consider some examples. If E is finite set and R is all subsets of this finite set, nu be a counting measure on the set E. Hence, the space H of square integrable function with respect to counting measure is a finite dimensional complex space C in power D. Any semigroup in this space is given by the following expression, where L is arbitrary D matrix. On the space of trajectories with values in this coordinate space, the measure mu is defined by the following expression. This measure is introduced in the book by academician Maslov, and if the group U is unitary, then this measure is called complex Markov chain. If the mapping U is stochastic matrices, then it is usual Markov chain. In general case, it is the following. And finally, let us consider the initial value problem for the retarded functional differential equation. We prove that this equation generates the semigroup in the following Hilbert space in the Sobolev space, and this Sobolev space can be presented in the following form, since according to embedding theorem, the limit value of any function in 0 point can be expressed the continuous function from representing the function from the Sobolev space by the following way. And our Hilbert space is the following, and this Hilbert space is the Hilbert space of square integrable function on this segment with respect to the measure lambda 0, where the measure lambda 0 is the sum of Lebesgue measure on this segment with delta measure in the point 0. This delta measure gives the following part of this Hilbert space. And the initial value problem generates C0 semigroup in this space. This C0 semigroups U generates the measure mu on the space of trajectories in with values in this coordinate space. This measure is given by the following expression. In the Feynman-Katz formula to describe the perturbation of this semigroup by the potential, where potential is any function from the space L infinity on this coordinate space with respect to measure lambda 0. And finally, we study the initial value problem and semigroup generated by this the initial value problem for retarded functional differential equations. We analyze the bijection between the measures and operator valued functions, and we have the problem to reconstruct the Feynman-Katz formula for the perturbation of the semigroup, which is generated by functional differential equations. Dear colleagues, thank you for your attention to my report.